All right, in our 8.3 video, we are going to be graphing reciprocal functions. So what a reciprocal function is, by the way, is something 1 over a of x, where a of x is some sort of linear function. So when we say reciprocals, like the reciprocal of 4 is 1 over 4, so the reciprocal of kind of a normal function looks like this. So that's what we mean by reciprocal functions. The majority of it takes place in the denominator. All right, so it's kind of like that fraction sort of idea that we've been looking at the beginning of this fraction, or the beginning of this chapter so far. So just like I do every time that we start by graphing something, I'm going to give you all the details of what we call the parent function, and then of course later we're going to learn how to transform them by shifting them left, right, up, down, any sort of stretching, really similar to the exponential and log graphs that we just did in the last chapter. So our parent function, kind of the original reciprocal function, is a very simple 1 over x. We just keep a 1 in the numerator, and then a of x, just about the simplest function we can make it, is just an x. So that's the parent function, and then any sort of transformation, like I said, will occur from that graph. The type of graph it is, it's called a hyperbola, which is just the name of a shape that you probably don't know yet, kind of like a parabola or something like that. A hyperbola is just the name of this particular shape. The domain and range. The domain is that x can be anything except for 0. And if you look at this, that would be because if we plugged in 0, we'd have 0 in the denominator, and we know we're not allowed to divide by 0. And then the range is that y can be anything except for 0. And same thing, same reason there. If my numerator is 1, no matter what you divide it by, 1 over something is never going to reduce down to 0. So I'll never get my function down to just 0. I have asymptotes. We talked about asymptotes with logs and exponentials as well. And because of these domain restrictions, it means I have asymptotes at x equals 0 and at y equals 0. So those are going to be those dotted lines that your graph can get really close to. It'll approach them, but you won't actually cross over that line. And then there are no intercepts at all. Okay, and we already talked about how it's not defined for x equals 0. That kind of falls into this category and this category. So let's see what the graph looks like. Okay, so this vertical line right here is an asymptote. So technically, you've got a dotted line right there that your graph is going to get really close to, but won't actually touch. Same thing at y equals 0. That's a horizontal line. And then we've got 2 points, 2 very important points. So you know when we were doing log and exponential, we always had our original points. So that's what we can do here. So say we plug in 1. If we plug 1 into this function, 1 over 1 would just be 1. So I have the original point 1, 1, which I can plot right here. And then if I plug in negative 1, 1 over negative 1 is just negative 1. So I'll also have the point negative 1, which is right here. So what a hyperbola does, it actually splits my graph up into 2 different pieces because I can't cross over this line, I can't cross over this line. What this graph does, it kind of takes on like a boomerang sort of shape. It comes like this down this line, curves around, goes through this point, and then it goes right along that line. And then we have a very similar one over here. It goes like by the asymptotes through that point and then drags along like that. So that is what your shape is going to look like, and every single thing that we're graphing today is going to take on this sort of shape. All right, so let's look at some examples. So we just talked about the domain. The only domain values will be where the function actually exists. And so if our denominator is equal to 0, then the function wouldn't be defined there. So what you can do is take whatever is in the denominator and just note that it can't equal 0. Okay, so my denominator is not allowed to equal 0. So with this, since it's a quadratic, I would solve this by factoring. So I can start with x and x to get my x squared. And then for these 2 pieces, I want to multiply to negative 24 and add to 5. So that would be a positive 8 and a negative 3. So when I set these both not equal to 0, I would come up with x can't equal negative 8 and x can't equal positive 3. So these would be the values where my graph is not defined. It's not defined at negative 8 and it's not defined at 3, but otherwise it would be defined everywhere else. Okay, for example 2, let's talk asymptotes and domain and range. So asymptotes, remember, are those dotted lines that your graph would get really close to but can't actually touch. So first of all, if you're looking at this denominator, we can do a similar sort of thing as we did up here. That x minus 3 is not allowed to equal 0. So if you added a 3 to both sides, we would find that x is not allowed to equal 3. And if you look at 3 right here, you can see that there actually is an asymptote right there. Okay, so the next thing we would look at is any sort of horizontal asymptote, which you can see is right about there. That's a line that your graph is getting really close to but not touching. So that happens to be at -2. And if you look right there, I've got a -2 on the end of my function. Okay, so for my range, this right here is my domain. For my range, according to this dotted line, I would say that my y value cannot equal -2. Okay, so this is my domain, this is my range. You base that off of those dotted lines. And then my asymptotes, we have what we call a vertical asymptote. And a vertical asymptote is just that vertical line that we drew right here. My graph has a vertical asymptote down the line x equals 3. And then my graph has a horizontal asymptote down the line y equals -2. So notice something that we've been talking about with logs, exponentials, basically every type of function that we've ever graphed is that x always does the opposite of what it looks like it's going to do and y does the same. So when I have x minus 3, it actually turns out my vertical asymptote is at +3. And when I see this -2 on the end, my horizontal asymptote actually is at -2. Okay, so this one, I can use that same logic to come up with my domain, my range, my vertical asymptote, my horizontal asymptote. So basically, you can see this connection between domain and vertical asymptote and the connection between the range and the horizontal asymptote. Okay, so this one, if we look perhaps at the vertical asymptote first, that would be this vertical dotted line that you could sketch in here, and that looks like it's at -1. And if we look right here, since I have x plus 1, we know that x always does the opposite. So that dotted line that I just drew in is the vertical line x equals -1. And then the horizontal dotted line that I could draw in seems to be right about here. And that is right through 5, which if you look, there is my 5 on the end. So y equals 5 is my horizontal asymptote. So the way that you do the domain and range, all you do is you cut out this one value. So my domain is every single x value except -1. And my range is every single y value except for +5. So basically just looking at the function will tell you those domain and range values. Same thing with the asymptotes. Okay, so my transformations, I've got these same values a, h, and k that you're probably used to by now between parabolas, square roots, logs, exponentials. So h is the horizontal translation. K tells you about the vertical translation, and then A is the orientation and shape, meaning any sort of flipping, stretching happens because of A. So H is the horizontal translation. Remember, it does the opposite of what it looks like it's going to do. So if you see X minus H, your graph is going to shift H units to the right. So most importantly for this horizontal translation is that your graph is going to move its vertical asymptote. Okay, so you're going to have a vertical asymptote at x equals h. And then if you have x plus h, remember x does the opposite, so your graph is going to move h units to the left, which means that you will have a vertical asymptote at x equals -h. All right, so basically the translation, what it will do is move your asymptotes, either left, right, up, or down. So now same thing with k. If you have a plus k at the end, that's going to move your graph k units up. So it's going to move your horizontal asymptote to the line y equals k. So it kind of starts out at 0, but if you move it up k units, your horizontal asymptote is going to move with it. And then if you see a minus k on the end, y does what it looks like it's going to do. So your graph will move k units down. And then your new horizontal asymptote will be at -k. The default was 0, but if you move it down, that horizontal asymptote goes down with it. And then finally, A, the orientation and shape. If A is less than 0, your graph is going to flip. So basically, instead of being in this quadrant and this quadrant, your graph will now be in this quadrant and this quadrant. Sorry, ignore that. I did not mean for my pen to actually hit that. So flipping will make your graph look like this. Please ignore that little piece right there. If you've got A is greater than 1, it's going to be stretched. And we'll talk about how that affects your new points. And if A is a fraction, it's going to compress your graph. And again, we will talk about how that affects your new points, because you know A always ends up multiplying the original points to get your new points. So let's look at some quick examples here. 2 examples in number 3. So first thing that we're going to do, we need basically 4 features of our graph. We need the horizontal asymptote, the vertical asymptote, and then we're going to transform our points. So our horizontal asymptote is going to be y equals, and it's always whatever number you see on the end here. So for us, it would be -3. If you didn't see a number, it would just be 0. The vertical asymptote is x equals the opposite of whatever you see down here. So this is going to be -1. So from my original graph, it shifted down 3 units and to the left 1 unit. Okay, so now for points, my original points are 1, 1, and -1, -1. So I'm going to transform and get my new points. Okay, so the x plus 1 means my x values are going down 1. I'm subtracting 1 from my x values. So that's what I get for my new points. And then for my original points, 1 and -1, this is still just a 1, so you don't have to multiply by anything, but technically you could say you're multiplying by 1 and then subtracting 3. So 1 times 1 is 1, minus 3 is -2. -1 times 1 is -1, minus 3 is -4. Okay, so those are my new points. So I'm going to plot 4 things. Dotted line, point, point, and then connect the dots. Okay, so my dotted line will be down here. This dotted line will be over here. And then plot these points. So 0, -2 will be right here. And then -2, -4 will be right here. Okay, so remember your graph kind of does this boomerang shape, goes along the asymptotes through the point, looks like that. Okay, so that's our first reciprocal graph. Let's look at this second one right here. Okay, so my horizontal asymptote is y equals whatever that number is. So for us, it's -1. My vertical asymptote is x equals the opposite of that number. So it's going to be 2. And then I get my 2 points. So my original points are always 1, 1, -1, -1. And when I transform them, I do transformations the same way I did with logs, exponentials, with all sorts of other things. So my x values, when I see x minus 2, I do the opposite. So I'm going to add 2 to my x values. So this one becomes 3. This one becomes +1. And then I take this y value. First, I multiply it by this number and then subtract 1. So 1 times -4 is -4. Minus 1 is -5. And then -1 times -4 is +4, minus 1 is 3. So those are my new points. Let's plot them. So 4 features. First, my horizontal asymptote. Next, my vertical asymptote. And then my 2 points. 3, -5. I'll be right there. 1, 3. Be right here. Okay, so what I'm going to do, drag along here, go through this point, and then along that line, same thing here. Come here, and there we go. Whoops, that was not a very good one. This, because of the negative, remember it flips to the other 2 pieces instead of being in these 2 pieces, and the stretch of 4 means instead of being super tight into this intersection right here, it's going to be farther away from this intersection. All right, so we're going to skip example 4 just in the interest of time, and that is 8-3.